And the big advantages are, well, better decisions, mainly because the AI can chew through way more data to build those models and constraints.
Right.
Plus, it cuts down on the human effort, saves time, saves money. The book mentions case studies, though not in detail in these excerpts, about streamlining operations, using data smarter.
Makes sense. Okay, shifting from business ops to, well, something vital for everyone, agriculture. AI and farming, we hear about it a lot. What's the main application we're looking at here?
I think one of the most impactful areas is predicting crop yields. Factors like weather, soil conditions,
Uh-huh.
and give farmers a much better estimate of what they'll actually harvest.
That must be incredibly helpful for planning. How does it help farmers day to day?
Oh, it's huge. Better predictions mean smarter choices about what crops to even plant in the first place. It also helps them manage resources, seeds, fertilizer, water more efficiently.
Less guesswork.
Exactly. And it's risk management too, right? If the forecast looks dicey because of weather, maybe they look into insurance or diversify their crops more.
So it's about action, not just prediction. Are there specific examples of AI tools being used?
Yeah, quite a few things are happening, like systems that adjust watering or fertilizer in real time based on sensor data, using satellite images to monitor crop health over big areas,
Wow.
image recognition to spot pests or diseases early, even analyzing market trends to help decide when's the best time to sell.
That's quite the toolkit.
It is. But it's crucial to remember these tools are only as good as the data you feed them and the algorithms behind them, quality in, quality out.
Always the case with data. Now, the text mentions something called QNN models, quantum neural networks, in agriculture.
Yeah, QNNs. It's pretty cutting-edge stuff. Researchers are developing these models specifically for ag yield predictions. They take in multiple data sets, things like humidity, soil moisture, lots of variables.
Okay, and how do they get the data ready for these QNNs?
There's a process. First, they merge different data sets. Some might be categorical, like the state or district, others continuous, like temperature.
Right.
Then they do something called one-hot encoding for the categorical stuff, basically turning names into numbers the model can use. And finally, they split the data, some for training the QNN, some for testing how well it learned.
Got it. Preparing the data is key. What does the whole system architecture look like?
It's multi-part. You've got the main ML model component. That's where the pre-processing, training, saving the model happens. Then a flashed backend, sort of the engine room that takes new input and gives predictions using the trained model.
Okay.
There's the front end, what the user actually sees and interacts with. And a Node.js backend managing things like user account and storing data, often in a MongoDB database.
Sounds pretty robust. And it mentioned the QNN is good with location data.
Exactly. Because things like state and district are categorical, the QNN handles that well, which is perfect for agriculture since location matters so much. So the whole system aims to forecast yield based on location, temp, season, rainfall.
Mm-hmm.
And it even has potential for using real-time weather or GPS, maybe even adding alerts for plant diseases down the line.
Very cool. Okay, let's move into healthcare. Analyzing ECG data, detecting heart problems earlier sounds critical. How's deep learning helping there?
Well, the goal is definitely early detection of cardiovascular diseases using ECGs, those heart rhythm recordings. Traditional methods aren't perfect, right? So now machine learning is being applied directly to ECG datasets to spot things like myocardial infarction, heart attacks sooner.
And what kinds of AI models are they using? The text named a few.
Yeah, they've tried some well-known deep learning classifiers like AlexNet, ResNet 18, VGGNet 16. Plus, researchers often develop their own custom CNNs, convolutional neural networks.
Okay.
And then they compare them, looking at accuracy, but also at things like loss curves, which kind of show how well the model is learning during training.
And the results. How accurate are these deep learning approaches for ECGs?
Pretty promising, actually. The text points out one study where an ANN model artificial neural network hit around 98% accuracy.
Wow, that's high.
It is. The others like ResNet, AlexNet, VGGs were also very good, around 96, 97%. So definitely showing strong potential.
A big improvement potentially. It also mentioned fuzzy-based approaches. What's that about?
Fuzzy logic. It's a different way for computers to handle uncertainty, dealing more with degrees of truth, like sort of high instead of just high or low. For ECGs, the idea was to classify parts of the signal into different levels.
Interesting.
Initial work was done, but the text notes that so far these fuzzy methods haven't really beaten the standard classifiers like neural networks in terms of accuracy. Still an area of research, though. Might be useful if data is incomplete.
Right, exploring different avenues. And it also mentioned backpropagation and wavelet decomposition.
Yeah, more tools in the toolbox. Backpropagation is fundamental to how most neural networks learn. It's how they adjust themselves based on errors. Wavelet decomposition is a technique to break down the complex ECG signal into simpler parts, different frequencies, to pull out key features. Okay. One study mentioned combined those and got 97% accuracy. But interestingly, as we said, that simpler ANN model actually edged out the others in the comparison, reaching nearly 98%.
Fascinating. So it's clear data is the fuel here. The next section talks about a data-centric approach. What does that really mean for deep learning?
It's a key distinction. Deep learning models are often more complex, so they tend to need more than just the raw data compared to simpler ML models. They often need more metadata, more context. And a big challenge is when you don't have much data, or when the model acts like a black box, you can't easily tell why it made a certain prediction.
That lack of explanation, the black box problem, that can be worrying, can't it? Especially for important decisions. So what's key to this data-centric view?
Data quality is paramount. Cleaning the data, verifying it's accurate. Because if you train a powerful model on garbage data, well, garbage in, garbage out, right? Things like data pollution, bad, or misleading info getting in can really mess things up.
Yeah.
So having good information governance, systems to ensure data reliability, that becomes really crucial.
We need ways to trust the input. The text mentions information confirmation systems.
Exactly, like fact-checking, but for the AI's data sources. As AI gets embedded deeper, we need that verification. And this ties into the whole growing field of AI ethics, doesn't it? Especially fairness.
Ah, yes. Fairness in AI, that's a huge topic.
It really is. The text mentions examples like the Comtast tool used in the justice system, potential biases in hiring algorithms, image recognition, even chatbots. These systems can unfortunately inherit and sometimes amplify societal biases present in the data they're trained on.
So, how do we measure or think about fairness in AI?
The deep dive brings up three fairness principles: independence, segregation, and sufficiency. They relate to different ways of ensuring fairness, like making sure predictions are similar across different groups, or that the model treats groups equitably or achieves similar outcomes over time. It also touches on individual accountability, making sure the AI's predictions are fair to each person, not just groups on average.
That seems incredibly complex to achieve in practice.
It is, and there are technical approaches being developed, like something called decentralized resilient optimization, aimed at improving fairness in these systems. But fundamentally, it often comes back to the data. It might need reorganizing, using massive datasets strategically to make better decisions and anticipate future issues.
So, data analysis isn't just for training models, but for planning things like logistics, HR, marketing research, even government operations.
Absolutely. But strategic decision-making itself has challenges, right? Often limited information, lots of uncertainty, trying to balance short-term need with long-term goals.
Definitely.
And that's where the text mentions multidimensional techniques being suitable methods designed for complex problems with lots of factors and often conflicting objectives.
Okay, let's shift focus again. Analyzing land use change with satellite images and AI. Why track this, especially in farming regions?
Understanding how land is used over time is super important for predicting trends and making good decisions about managing agricultural resources. Seeing if farmland is expanding or if cities are growing into rural areas, that kind of thing.
The text brings up shift in cultivation. Can you explain that?
Sure, it's a traditional farming method you see at places like northeastern India. Farmers clear a patch of land, often by burning vegetation, farm it for a few years, then leave it fallow to recover while they move to a new plot. It's a cycle.
Okay.
And using satellite images from different times, combined with AI analysis, gives a much clearer picture of where this is happening, how widespread it is, and maybe even predict if it's likely to continue. The research mentioned used Landsat and ResearchSat-2 data, employing segmentation techniques to spot these shifting cultivation areas, for example, in the East Garo Hills of Meghalaya.
So, from satellite views down to individual plant leaves, the next bit is on detecting crop leaf diseases using deep learning. That sounds very practical.
Oh, extremely practical for farmers. Leaf diseases can wreck a harvest, so catching them early is key. The deep dive looks at two specific deep CNN models, Yellowvate and ResNext T50. Both are known for being really good at image recognition tasks, like finding objects and classifying them, in this case, spotting diseases.
And there's a specific system mentioned, Leafine.
Yes, Leafine. It's presented as a deep learning tool designed not just to detect the leaf disease, but also to suggest appropriate manure or fertilizer based on what it finds.
Oh, interesting. So it offers a solution too.
Kind of, yeah. To build it, they created a custom dataset over 4,000 images of plant leaves, some healthy, some showing common problems like blight, leaf spot, powdery mildew, or nitrogen deficiency. They gathered these themselves and also used images from other existing datasets.
And how did they prepare these images for the AI?
Standard pre-processing steps, really. Rescaling and resizing them all to a consistent size, 512 by 512 pixels in this case. Then normalization, adjusting the pixel values after converting them into a format called PyTorch tensors that the models can work with.
Okay, and how do those models, YOLOV and ARSNX 50, actually work in this Leafin system?
Well, YOLOV is known for speed and accuracy in object detection. They mentioned tweaking its initial layer slightly. ResNex 50 uses a clever architecture with parallel pathways to analyze image features efficiently, and they made a small change in one layer to help it train faster. The results suggested these models achieved good precision in Leafine, though it did take some upfront work getting the images ready.
Right, the data preparation again. Okay, we touched on ECGs, but the deep dive revisits medical diagnosis, adding puberty disorders. What's the link there?
So for ECGs, it reiterates the success, especially of that ANN model hitting nearly 98% accuracy for detecting heart attacks, outperforming simpler CNNs and others like ResNet in that context.
Okay.
Then it pivots to central precocious puberty, or CPP, when puberty starts unusually early. Traditional prediction methods have limits, so the aim is to use machine learning, specifically ensemble techniques, to predict CPP, identify risk factors for puberty issues and maybe later infertility, and potentially guide treatment.
That could make a huge difference for kids and families. Why machine learning for this?
Well, the idea is to create a pre-screening tool. The standard test for CPP, the GNRHA test, can be costly and invasive. If ML can identify high-risk kids earlier using less invasive data, that's a big win.
Makes sense. What ML methods are they exploring?
They mentioned XGBoost, that's a type of gradient boosting, very powerful. Also, random forest, which uses lots of decision trees, and SVMs support vector machines.
And what kind of patient data fuels these models?
Clinical records, things like age, height, weight, BMI scores adjusted for age, obesity status, Tanner stages for pubic hair, whether menstruation has started, bone age versus actual age, ultrasound measurements of the uterus and ovaries, follicle presence. Quite detailed stuff.
Wow, yeah.
The text also briefly notes some related research in India looking at how obesity and even air pollution might impact puberty timing and periods.
Complex interactions. Okay, moving from health to security, weapon and helmet detection using deep learning. A critical area.
Definitely. And detection methods have evolved, right? From early X-ray systems to 3D CT scans and now real-time video surveillance. Traditional ML used features like Harris interest points, but deep learning, especially CNNs, became the focus.
But early CNNs were slow.
Yeah, the sliding window approach, checking every little patch of the image, was computationally heavy. That led to two-stage detectors like RCNN and faster RCNN. They first proposed regions likely to contain an object, then classify those regions. Faster RCNN, trained on custom data with a VGG16 base, apparently worked well.
Are there faster options now?
Yes, one-stage detectors like YOLO, RetNet, and SSD came along. They do the localization and classification in a single step, generally faster.
Do these systems only look at visual appearance?
Mostly, yeah, but some research is trying to add context, like using thermal imaging for metal weapons or analyzing body posture.
Interesting. And the text describes a specific proposed architecture.
It does, one using Darknet 53, which is often associated with YOLO, but with added residual blocks, and something called a dense architecture. It's designed to spot multiple guns and helmets in real-time video.
How does that proposed system work step by step?
Okay, so the algorithm basically initializes a camera, grabs frames. It first looks for helmets if found. It issues a warning to remove it. Then it looks for weapons. If it detects a weapon over several consecutive frames, it increments a counter. And if that counter hits a threshold, it triggers a suspicious activity warning.
So it needs confirmation over time.
Right, to reduce false alarms, presumably. Some systems also use shape features in PCA, a dimensionality reduction technique, to help with detection.
And the performance of this proposed system.
Reportedly very high 99.31% accuracy for both guns and helmets. The text claims it outperformed various YOLO versions, V3, V4, V5, and older methods like hot cascade, SVM, decision trees, KNN, both in accuracy and speed. There's even a confusion matrix shown, breaking down the predictions.
Impressive results claimed there. Okay, next up, image processing for edge detection. Why are edges so important?
Edges are fundamental for image understanding. They define the boundaries of objects, the corners, the basic structure within an image. Finding them is often a first step at recognizing what's actually in the picture.
And how do we typically find these edges?
Mathematically, using gradient operators like Sobel, Pluit, Robert, also Gaussian operators, these look for sharp changes in pixel intensity.
Are there limitations?
Yeah, the gradient ones can struggle with diagonal edges and noise in the image. Gaussian methods are generally better if the image is noisy.
So how does this fit with other image cleaning techniques?
Edge detection often comes after applying filters like median, mean, Gaussian, Wiener filters, which are designed to smooth out noise and improve the image quality first. Makes finding the real edges easier.
Okay. And the text introduces another specific network.
Right, a fuzzy flexible deep convolutional network, or FFDCN, specifically designed for edge detection. They trained and tested it using a standard benchmark, the Berkeley segmentation dataset.
And how did this FFDCN stack up?
They compared it against SVM and a standard CNN using various metrics. It apparently performed well, particularly getting a high SSM score structural similarity index of 98.04%. That suggests it was very good at matching the true edges in the test images.
Okay, switching gears dramatically now to finance, AI and ML for market volatility and stock price prediction, focusing on India.
Yeah, finance is a huge area for AI. Volatility, how much prices swing is key. There are traditional econometric models like ARCH, GARCH, and variations like EGARCH, TGARCH, designed to capture this kind of clustering volatility you see in markets.
Right, prices tend to have calm periods and jumpy periods.
Exactly. These models try to predict future volatility based on past price swings. The text notes these have been studied, maybe less so specifically on the India market. It also mentions XGBoost, that powerful ML algorithm being used for prediction tasks here too.
And how are they applying these to actual stock prices? It mentions Rain Industries.
Yeah, the research applied models like ARIMA, which looks at time series patterns, GARCH, ARCH, and XGBoost to analyze and try to predict the price movements of that specific stock Rain Industries.
Are they also using the deep learning networks we've seen elsewhere?
Yes, definitely. CNNs and LSTMs, long short-term memory networks, are mentioned for stock price predictions. LSTMs are often favored for time series data like stock prices because they have a kind of memory that can capture longer dependencies.
How do they know if the predictions are any good?
They use standard error metrics like MSE, mean squared error, MAE, mean absolute error, RNSE, root mean squared error. Sometimes they might also use financial metrics like the Sharpe ratio, which measures risk-adjusted return. The whole process involves training, validating, predicting the future, comparing to actuals, and then doing sensitivity analysis, seeing how changes in inputs affect the outcome.
A thorough process for a notoriously difficult prediction task. Okay, from finance to retail. AR comparing e-commerce and traditional stores. Shopping has changed so much.
Hasn't it just? Customer attitudes to online shopping have shifted massively. Social networks are huge influencers now. This puts pressure on brick-and-mortar stores to adapt.
How are physical stores responding?
We're seeing more tech in stores, ways to interact with customers, gather insights on behavior, and many are going for an omni-channel model, right? Integrating online and physical experiences to meet customers wherever they are.
Makes sense. The deep dive mentions a qualitative study in Kolkata, focus groups and interviews.
Yeah, they talk to customers using focus group discussions, FGDs, and retailers using depth interviews, DIs, to understand why people choose online versus physical stores. They identified key themes and sub-themes.
What were some themes from the customers?
Convenience was big things like payment options, delivery speed, but also trust-based purchase, which tied into the ability to touch and feel products, get demos, ask questions directly, that personal touch and advice. Also, specific needs for certain products, like checking expiry dates on medicines in person.
Interesting mix. And from the retailer's perspective.
Retailers also hit on convenience, but framed it around the strengths of the physical store, building trust,
Welcome to the deep dive. Today, we're taking a really fascinating journey, actually, into the practical world of deep learning. We've got some great insights from a book called Deep Learning Applications and Operations Research.
Yeah, it's a 2025 publication. And our goal today really is to explore how this tech, deep learning, part of AI and machine learning is actually being used out there.
Right.
In, well, a surprising number of fields. We're looking at how it helps make sense of data, how this tech, deep learning, part of AI and machine learning is actually being used out there.
Right.
In, well, a surprising number of fields. We're looking at how it helps make sense of data, classify things, spot patterns, predict trends.
So think of this as like getting a grip on some pretty advanced stuff, but without getting totally bogged down in the jargon.
Exactly. We want you to understand the impact. And just to give you a roadmap, we'll touch on operations research, farming, healthcare like ECGs, and even puberty disorders, how we shop, EV charging,
Wow.
security, image stuff, even the stock market. It's quite a list.
It definitely is. Okay, let's dive in. Operations research, or OR. What's the core idea there?
Well,